Everybody has been telling me lately that I need to shift left in my engineering work process. You need to shift left, Amelia. I know binary. Doesn't shift left mean multiply by 2? I can't even get my current engineering work done, let alone double. But no, and then they say I need to be more agile. What? I can touch my toes. I don't think I can do a handstand or that yoga thing where you put your legs behind your ears. But what does all of this parkour nonsense have to do with my design project? Hi, I'm Amelia Dalton, host of Chalk Talk. As a hardware designer, do you find all this left shifting and agility stuff as confusing as I do? Well, let's try to clear that all up, shall we? My guest today is Jack Erickson from MathWorks, and we're going to talk about how to do agile hardware development. Before we get started, don't forget to click that link. There you can find out more about agile hardware development from MathWorks. Hi, Jack. Thank you so much for joining me today.
Oh, thank you.
So I see shift left in your title. Is this shifting left with a carry or what, Jack? What is really driving this whole shift left business?
Sure. So traditionally, semiconductor technology has driven the applications. Think about a more powerful mobile processor, gives you all these fancy smartphone capabilities.
Yeah.
But these days, it's really the applications that are driving the semiconductor technology. Think about ADAS systems or massively parallel communication systems, industrial robotics. These are all very advanced technology that require a lot of innovation over on the left.
Right.
And they require the semiconductor technology to support them.
Okay, so these applications are driving semiconductor technology, but I've been seeing quite a few traffic jams on that highway lately, Jack.
So yes, ASIC and FPGA projects can be very resource intensive. Mentor Graphics has commissioned these studies every couple of years with Wilson Research, and you can see that around 60% of chip design projects are behind schedule.
Wow, okay.
Yeah, and that number's been growing. A big part of it is coming from verification. When you look at the amount of engineers required per project, and these numbers here from the same survey for ASIC in particular, but FPGA is a similar ratio.
Okay.
Design engineers per project are growing, but verification engineers are growing even faster.
Yeah.
And to make things worse, those designers are spending about half their time doing verification themselves.
Eek, okay. Okay, Jack, so we talked about applications and then we jumped to semiconductor design. How do we bridge the two?
Yeah, so there's a lot of work happening up at the system and algorithm level, designing these applications, these ADAS systems, these industrial robotics controls and sensors and so forth. And a lot of that is being done using MATLAB or Simulink. Unfortunately, what happens is the systems engineers then take all that work, they've designed and verified these systems up in the system level, and they then create a paper specification. So they try to capture all their requirements and they write it in a document that the design and verification engineers go off and dutifully try to match.
Sure.
And where that breaks down is, first of all, the algorithm design is happening really with no sense of the hardware. So it can be suboptimal in terms of what gets put in hardware versus what gets put in software, or even how the hardware is broken up across devices.
Sure.
And when you are writing and capturing the specification document, you can make a lot of assumptions that you figure the downstream engineers understand what I'm talking about.
Sure.
And that can lead to a spec that's incomplete. The downstream engineers may interpret it a different way, and then you run into some big problems.
Yeah.
And when they are writing their RTL, they have a limited ability to explore different architectures. So if they get something that's really difficult and challenging to fit in onto an ASIC or onto an FPGA, they have very limited recourse at that point. And all the work that's done in terms of verifying up at the system level, they're running system level simulations, none of that work is really leveraged going forward. So everything has to be started from scratch in the verification project down in the hardware design team.
Right.
And as you can imagine, this is all very resource intensive because essentially you're just restarting the entire project from this Word document that was handed on down from the systems team.
Right.
And the way this plays itself out is when you look at the root cause of functional flaws in designs, you can see that the ones that are the largest and growing the fastest really have a root in that specification-driven process where you have manual design errors for manual coding or the spec changes. And it's either not communicated well or the design team can't react fast enough, or of course there's that incorrect or incomplete specification where you had those assumptions made.
Okay, so this sounds nice and all, but it seems like there's an awfully large chasm to bridge here. Are we going to need a boat, Jack, or a kayak maybe?
Hopefully not a kayak. So yes, this is a pretty large chasm to bridge. And what we really propose is a collaboration environment between the systems level engineers and the hardware engineers.
Okay.
Really, the benefits that they can achieve is, what if the engineers could collaborate in the same environment to take that system level design and refine it toward what we call an implementation architecture, something that's ready to be generated as hardware automatically.
Okay.
By working at a higher level, the hardware engineers can now explore a much wider variety of architectures to try to meet their design goals.
Okay.
And then they can quickly make changes if the spec changes or find a bug or something. And then they can re-verify right at the system level and then just automatically generate their RTL.
Nice.
And of course, automatically generated RTL is going to reduce the burden on the verification team because you don't have those manual coding errors and the bugs that arise because of an incomplete specification. And one nice piece about this too is the ability to reuse the models from the system level to really bootstrap your verification environment.
Okay, so I think I get this concept, but can we take a closer look at what this really looks like?
Sure. Really starting off with MATLAB and Simulink, they're very widely used to start chip design processes.
Yeah.
But they're really operating at the algorithm level. If you think about, say, an image processing design where you need to do some edge detection on a stop sign.
Okay.
That's all nice in MATLAB and Simulink. We can work on that on a frame at a time. But in hardware, of course, you are streaming bits in.
Right.
So in this image processing example, we're streaming in the rows of pixels one at a time. And so if we want to scan for the edge of the stop sign, we need a window to look at. And in order to look at a window in the hardware side, we need to store, say, a couple lines of those pixels, what we call a line buffer.
Okay.
So we need to take those system level algorithms that operate on the frame level and convert those into what we call hardware friendly implementation architectures that are streaming bits and bytes in and operating and working at that level. So and so I can show you what this looks like in this collaboration environment. So as we come in, the design's already simulating. And this is an image processing algorithm that's doing some corner detection. It's panning across a variety of images and adding corners, as you can see in red. We can specify our RGB values and the transparency value you see there. So the image source is coming out as frames, and we need to convert those to pixels. And so we have this nice block here that converts frames to pixels for any size frame, and it adds the front porch and back porch and the control signals that go into it. And of course, on the other side of the FPGA, we have its counterpart, the pixels to frames. So inside the FPGA, you can see we have our pixel and control signals coming in and going through the various stages of image processing. This block here is interesting. This is a filter block, and you can see it's very high level, and it's just calculating a Gaussian filter, and you can play with the filter coefficients here and tune your design very easily. You can see here where we specify the line buffer size. So this is something that will get mapped automatically to memory. You don't have to worry about managing that and mapping it yourself. And just going through the design, some other interesting pieces. So at the end, we align the corners with the video and then we overlay them. And if we want to look in the overlay, now this was a lot of matrix manipulation and math, which is nicely done in MATLAB. So here we just reused our MATLAB code and we converted it to fixed point. You probably saw a lot of fixed point data types throughout the design. That's done automatically as well throughout the MATLAB and the Simulink. So at this point, what I'll do is I'll kick off a run that goes and automatically generates HDL code. And while that's running, we can switch back and talk a little bit about what this process does. So this is a tool we have called HDL Coder, and it automatically generates synthesizable Verilog or VHDL code.
Okay.
So because we are coming from this collaboration environment down into your traditional ASIC and FPGA implementation workflow, this allows you to stay connected. We have the ability to trace your lines of RTL back to the model that they came from and even back to the requirements document if you've set that up.
Nice.
And we optimize for ASIC or FPGA. We have automated flows set up for some of the more popular FPGA synthesis tools, but we can do optimizations for ASIC or any kind of FPGA.
Okay.
And because we're working in this high-level collaboration environment, as I mentioned earlier, you can easily explore architectures at a high level and then just go and generate your code. And because we're automatically generating the code, it eliminates those manual coding errors that pop up. The RTL that we generate is very readable. You'll see an example of that when we see our results. And we also do some rule checking, and we have interfaces with some of the more popular RTL lint tools as well, if that's something that you want to check.
Excellent.
So let's look and see if our results are ready here. So you can see a nice little report here, and we'll get back to that in a second. I want to show that RTL first. And so this here you can see is pretty well commented. It shows where it's coming from, and we've maintained all our I/O and wire names that we've set up in Simulink. Here we show where the component that this particular chunk of code is coming from, and you can see the H start and V start signals. Those are our control signals. But it's pretty well commented. It's very readable. And we also generate the FIFO and the RAMs and FSMs, things that you didn't see in that Simulink model. Those are getting generated automatically. Now, looking at our resource reports, we didn't really set any optimizations, so let's just look at the high-level resources. So I usually start with this and looking at things like the amount of registers and RAMs and multipliers can tend to be expensive. And it's broken down by hierarchy, so we can look at our multipliers to see where maybe we can improve things. There's some RAMs. If we look here, as a hardware designer, we look and we see a multiplier that's 36 bits, so that's probably going to have to get split across two multiply resources in an FPGA. So let's take a look. So now this is a gain block. It's multiplying the output of this square function by a factor of 0.04. So as a hardware designer, I look at this and say, well, what if I were to move this before that square function? So I multiply by 0.04 before I square it, then I wouldn't have that bit growth that outgrows the DSP slices. Something else I notice as a hardware designer are these Z with the -D blocks here that are everywhere. And those are basically, we went and manually inserted pipeline stages, just because as a hardware designer, you have an idea where they need to go. The tool can insert those automatically and will move them around and will balance them on parallel paths. But if you have a hardware designer collaborating with your system designer, hardware designer can know that, okay, a multiply is probably going to take a couple pipeline stages, so I'll just put those in here so we can simulate them, verify that at this level, and then let the tool take over and move those around as needed during implementation.
Okay, Jack, so automatic HDL code generation sounds great, but I'm always a little worried that auto-generated code isn't as great as my code.
Yes, we get that a lot, and it may not be.
Okay.
What's nice about this is it gives you the ability to explore at a high level.
Sure.
And really find a better architecture. There are always cases where your code, when you write it and you handcraft it, is going to be the best implementation. But there will also be a lot of cases where you chose an architecture and you got the best you could out of that architecture, but there were a couple other architectures out there that you didn't have the chance to explore.
Right.
And so that's the nice thing about this approach. And so we've had a lot of customers go through this, and these are all public testimonials that we have out there on our website. But Qualcomm India, for instance, they wanted to see if they could get the same die area for an ASIC as they could by hand. And it shows that they could with a lot less effort.
Yeah.
And that's pretty typical. We have customers like Faraday, where they were able to reduce their latency a little bit and their gate count by a lot by finding a better architecture.
Nice.
IFM Engineering was able to greatly reduce their resources in slightly less time. One of my favorites is this Nokia was doing an FPGA prototype of an ASIC, and by being able to explore different architectures, they were able to greatly reduce their clock period and pretty significant area savings as well.
So, Jack, what's the verification story here, especially if I don't write my own code?
Well, that's one nice part is by not having to write your own code, you reduce the risk of introducing errors.
Sure.
You're spending more time architecting your design and you automatically generate code so those manual errors are eliminated. And then in terms of getting the verification environment up and running, we can also generate models for the verification team.
Oh, okay.
So we can take the MATLAB or Simulink models and generate system Verilog DPI components. Now, MATLAB and Simulink have had the ability to generate C code for many years. The airplane that you last rode on or the car you rode in on probably has generated code for MATLAB or Simulink. So it's very mature and proven technology. And what we do is we wrap that in System Verilog DPI, which is a really nice interface because it allows you to just call your C code as if it were just a System Verilog module or function, really. You can use it natively within any System Verilog simulator. So we see customers using this to model their scoreboard, so model the golden reference in their scoreboard.
Sure.
Sometimes they'll export stimuli from their MATLAB or Simulink and use that as a stimulus to just get up and running more quickly. If they have analog components or other system level kind of foreign components for System Verilog, we can model those and import those into System Verilog as well.
Cool.
The way this works is it will just right click and it will automatically build a shared library and System Verilog interface, and it will generate all the C code and make files and everything you need in case you're not building on the same platform. You can take that and go to a different platform and run the make files.
Okay, so Jack, this is pretty different from my usual engineering process. How do I get started?
Yeah, it is very different. We've had a lot of customers go through this. We've worked with a lot of customers through this. I can give you an example here. I can walk you through an ASIC customer.
That would be great.
This customer, fairly typical, where they have a separate systems and research division that is really responsible for the product itself. And then they have a division that's doing hardware design and verification. And so the systems division was doing their design mainly in MATLAB, and they were handing over a written specification to the hardware team. Then the hardware team would have to go and basically manually recreate everything with RTL, with C code for their reference models in their test bench. And then they would go run their traditional synthesis and verification and hand it back over to the systems team for them to prototype in the lab.
Right.
What was happening with them is that it was taking a long time to read and interpret the spec and to write the C and the HDL code for the test bench and the design respectively. And because it was a manual effort, errors were being introduced. And the worst part was that bugs were being found by the systems team when they got that FPGA back in the lab. And by then it's way too late. So they were looking for help. And we identified that they didn't have this collaboration environment between the two teams. So we started them off by really getting them onto MATLAB together with Simulink. So you saw in Simulink, it's a graphical environment, which is nice for seeing the hardware architecture. And you can also import your MATLAB code into that. And they would hand that over along with the specification. So now they have both the written spec and an executable spec.
Okay.
And so then they can run that and test things. And then that eliminates a lot of the misinterpretations due to assumptions.
Sure.
So it fills those holes. And because the verification team was the one most in pain, it was easiest to get started by just generating these System Verilog DPI components. And that helped them get their test bench up and running much more quickly with more accurate models too than writing the C code by hand.
Nice.
So once they got through that project and they were comfortable with it, they were comfortable with using Simulink, then they started doing things like fixed point conversion and generating HDL to really drive the design side of things. So the next project, they were auto-generating both the verification models as well as the RTL models that went into their traditional ASIC synthesis place and route workflow. And they were also able to take this at the RTL snapshot and use HDL Verifier also has an FPGA in the loop capability to co-simulate the design running on an FPGA board in your system context. And so they were able to get an early snapshot of that as well in the lab. This really saved them weeks of coding and debugging. It eliminated the bugs. And really most importantly is once they got a prototype back in the lab, it worked correctly.
Yeah. Awesome. So what are the products I should be looking for here, Jack?
We have MATLAB and Simulink, obviously, and these products work from within MATLAB and Simulink. With HDL Coder is what generates the HDL from the implementation model.
Yeah.
And that comes with a lot of blocks that we call HDL ready or HDL friendly.
Okay.
And for some of the higher level blocks, for instance, the blocks that you saw in that image processing design, we have Vision HDL Toolbox, which supplies those. And we also have a fixed point conversion product, Fixed Point Designer, which is really nice. It simulates your design and extracts the signal ranges and what precision will be necessary to maintain whatever level of fidelity that you'd like.
Nice.
And will automatically propose data types that you can then override or just accept and then go into HDL code generation.
Cool.
Yeah, so it's really nice in terms of it allows you to do these early architectural trade-offs, getting the hardware designers, providing input to the system designers and vice versa, and really getting them to collaborate and come up with a better design. And from there, it's just push-button automatic code generation rather than having this big, large manual effort that's just error-prone and costly.
Yeah.
The really nice part is it allows you to quickly adapt to changes. So if you need to target a different product requirement or a different process, or you get late-stage ECO requests or something like that, you can just make the change in the system-level environment, run system-level verification, and generate your code. So this really provides you with a much more agile hardware development and verification environment.
Very nice. Okay, so if I want even more information, where should I go?
Sure. So we have our handy-dandy product pages on mathworks.com. You can see the one here for HDL Coder, and you can see my smiling face there. You can always click on that button right below it to email me.
Very cool.
And for more in-depth information on what we see as the vision for this agile HDL development and verification approach, we have this article on EE Journal.
Imagine that.
It's my favorite publication that you can access at the URL that you see listed there.
Very cool. Well, I think that's all I have time for today. Thank you so much for joining me, Jack. This was super cool.
Oh, thank you. It was a pleasure.
And before we go, you didn't forget to click that link, did you? There you can find out more information about agile hardware development from MathWorks. For Chalk Talk, I'm Amelia Dalton from eejournal.com. For more Chalk Talks, head on over to the on-demand section of eejournal.com or check out YouTube, keyword EE Journal.